exponential and logarithmic equations. So the idea here is that we're going to have some equations. They're going to be mixed together. The exponential equations, and in order to solve an exponential equation, you have two options. One would be get the base the same, if that's possible. If that's not possible, then you're going to use a logarithm to solve an exponential equation. And if it's a logarithmic equation, the strategy would be to use an exponential to solve a logarithmic. So there, and remember that they are inverses of one another. So exponential equations you can solve with logarithms. Logarithmic equations you can solve with exponentials. So we're going to look at several different examples of this stuff and see what we can do in order to solve some equations using different strategies out of that. So let's start with something fairly simple. 8 to the x power is equal to 21. So we have a base of an 8 on this side and a 21 on the other side. And what tells us on this one, what we want to look for is look for shortcuts to solve these things. So I know 8 is 2 to a power, but 21 is not 2 to a power. So I know I can't get the bases the same. Okay, there's no way to turn an 8 into something that's a 21. There's no way to turn a 21 that's an 8 or a 2 for that matter. Okay, so I know I can't get the bases the same. So this is where solving using a logarithm is the method that you want to do. All right, so the trick to this is we're going to use a common log to solve this in order to get rid of the logarithms out of that. This is a standard practice for most textbooks. This textbook really uses the common log quite a bit. There are other ways to solve this. So like if you used if you Googled solving this particular equation, you're probably going to get several different ways of doing it. I'm going to show you the way using a common log, which works for most every problem. When you start doing a specific base of a log, then that changes for each problem. So what we're going to use is more of a generic way of doing it that will work for a wider range of problems. So that I think that's the best way to go about this. So what we're going to do is we're going to take the natural log of each side, because that's a common log. We could also do the log base 10 of each side, but I'm just kind of trying to do things as closely as to what the way our particular author of our textbook does things, and they tend to use the natural log most of the time. So that's what we're going to use. So when I take the natural log of each side, what that allows me to do is get the x out of the exponent and bring it down here to the front so that it's x times the natural log of 8 equals the natural log of 21. What you need to keep in mind is that the natural log of 8 and the natural log of 21, they're just numbers. They're decimal numbers. They're written a little bit better than decimals right now because they're not, you don't have to put point and then a bunch of stuff. But these are just numbers. So this is x times a number is equal to a number. It's kind of like if you had this problem, you had 7 times x equals 14. You would, to get x by itself, you would divide by the number you're multiplying by, right? So to divide, here for this problem, you would divide by 7 to get x by itself, right? On our problem, you've got a weird number. It's the natural log of 8, but it's a number. To get x by itself, if I divide by the natural log of 8, that'll cancel out on this side. And on this side, if I divide, what I divided by over there was the natural log of 8. That's going to end up being what x is equal to. X is equal to the natural log of 21 divided by the natural log of 8. And then we're going to get the decimal approximation for that as well. Okay, so with my calculator, I'm going to do natural log of 21, close the parentheses, divided by natural log of 8. And I'm going to go 4 decimal places, 1.4641. So we got the ones with the natural log in it, that's the exact solution. This is the decimal approximation. Be able to find both. It kind of bounces back and forth on each of those, which ones you need to do out of that. So here we had an exponential. we used a common log to get the variable out of the exponent and solve the problem. Okay. Let's say we had 11 to the x. Let's do 11 to the 2x equals 32. 11 to the 2x is equal to 32. All right, so I know I can't turn a 32 into 11 to some power, right? Because 11 squared is 121. That's way too big already. So I know that I can't get the bases the same. So I'm going to take the natural log of each side. And that allows me to bring this 2x down to be 2x times the natural log of 11 is equal to natural log of 32. So this one looks a little different. It's the same idea though. Okay. 2x times the natural log of 11. Well, what part are we trying to get by itself? X, right? So we're going to divide by everybody that's not x. So we're going to divide everybody by 2 natural log of 11. 2 natural log of 11. That's going to cancel the 2. To cancel the natural log of 11. That's leaving us x by itself. Natural log of 32 over 2 natural log of 11. This one's a little trickier to get the decimal approximation on because they got that 2 that's in the bottom there. So when you go to put that in the calculator, you're going to hit natural log of 32, close those parentheses, and then we need to put in parentheses 2 times the natural log of 11, and then close those parentheses up like that. That way it gets the 2 in the denominator and the natural log of 11 in the denominator. We get 0.0 or 0.722, and that's, we look at the fifth number, it's a 5 or bigger, so that means the fourth number goes up. So 7227 is the decimal approximation for that one. So using a common log to get that exponent with the variable in it down so that we can use division to solve. So here we had these are exponential equations that we're starting with, and we're using a logarithm to solve them. We're using that common log of a natural log to solve them. Okay. Let's look at a little bit more difficult one. Let's say we had 5 to the 2x minus 3 equals let's just do 8 to start with, and then we'll get one that's a little bit more, even more difficult than this. Okay, so this one has a little bit more complicated exponent. It's got 2x minus 3 in it. We know we can't get the bases the same because I can't take a 5 and make it an 8 as 5 to a power. If this were a 25 over here instead of an 8, then hey, I could change that to 5 squared. It's a much easier problem. But because it's an 8 over there, that means I'm going to have to use a logarithm to solve this. So what I'm going to do is I'm going to take the natural log of each side. Okay. And then I'm going to do the same step. I'm going to bring this exponent out to the front. So I've got 2x minus 3 times the natural log of 5. Okay. All right. Now, what property do we see here on the left side? You got parentheses times natural log of 5. Remember, what is natural log of 5? It's a what? It's a decimal number, though. It's just a number. In general, it's a some sort of number. So if we've got parentheses and a number outside, what property is that? You could distribute that number to both of those pieces. So I can take this natural log of 5 and distribute it across there and get 2x natural log of 5 minus 3 natural log of 5 is equal to natural log of 8. Okay, so what I've done is I've distributed the number across, and now I can start getting the part that has x by itself. What part has x? This first part does. So I need to move the part that doesn't have x, just like I would any other equation. It just looks weird because I've got this natural log business in here. Okay, so they're subtracting 3 natural log of 5. So to move it, I'm going to use what? Addition of the 3 natural log of 5. So I'm adding 3 natural log of 5 to both sides. And that cancels it out on the left side, gives us 2x natural log of 5 equals natural log of 8 plus 3 natural log of 5. Now, is x by itself yet? No. So that means I got to keep going. Well, what's going on over here with this stuff that has x on it? Well, I got a 2x natural log of 5. That's 2 times x times the natural log of 5. So how can I get x by itself? What's the opposite of multiplication? All this stuff over here is multiplying. I could divide by the 2 natural log of 5. I'm dividing both sides by 2 natural log of 5. That cancels out over here. Gives us x. Natural log of 8 plus 3 natural log of 5 over 2 natural log of 5. So it's a big fraction over there. Big ugly fraction. Looks like a bunch of stuff. But it's, remember, these are all just numbers. That's all they are. They're just numbers. They just look weird. Okay? Kind of like me. I'm just a math teacher. I just look weird. Okay? My cousin reminded me how much gray hair I have this weekend. It was wonderful. I love family. All right. And then so we're going to work that out. We're going to get the natural log of 8 plus 3 natural log of 5. And then we're going to divide all of that by 2 natural log of 5. So I'm going to do that in parentheses. Natural log of 8 plus 3 natural log of 5. 3 natural log of 5. Then I'm going to close up those parentheses. That's the top part. Okay. Divided by parentheses 2 natural log of 5. That's the bottom part. All of that stuff just turned out to be 2.1460. 2.1460. So that one's a little bit more difficult. Quite as difficult as the next one, but it's same idea though. So what we're looking at here is think about anything that's just a natural log with a number on it as a number. Don't think of it as something fancy. It's a number. That's all you got to think about. All right. Let's take example D. Let's say we had 3 to the x minus 5 equals let's do 10 to the x plus 2. All right, so with this one, a little bit more difficult because you got a variable in the exponent on both sides. Okay, so a little bit more difficult. Wouldn't be near as difficult as if this 10 were a 9, we could change the base to 3s and work this out, and it'd be a lot easier. But because this is a 3 on the base over on the left side and a 10 on the base on the right side, I can't get the bases the same. So that's when I know I've got to do a logarithm to solve it. Okay, so in order to do the logarithm to solve this, I'm just going to use a natural log of each side. And that's going to allow me to drop the exponent down to the front. So maybe as you've done several of these, you'll see, hey, I'm always going to move that exponent down to the front. It's going to make life easier. So you'll do that automatically and just kind of skip a step there. So we got x minus 5, parentheses, and then natural log of 3. Not plus sign, but equals. X plus 2, parentheses, natural log of 10. All right, so this one, you got parentheses and a number, and on the other side, you got parentheses and a number. Okay, so we're going to distribute. Same way we did on the last problem, but we're going to have to do it on both sides here. So that's what makes this one a little bit more difficult. It's got two sides. It's got a lot of work on them. So we got x, natural log of 3, minus 5, natural log of 3. On the other side, we got x, natural log of 10, plus 2, natural log of 10. Okay. So we've got to look at this and say, okay, let's think about this as if it were another kind of problem. Let's say it was this problem, 3x minus 15 equals 10x plus 20. If it were that problem, what things would you put together? If it were this problem that's up here on the right. Because why? They're like terms. They go together, right? They're plain numbers. On our problem, you got this 5 natural log of 3, and then this 2 natural log of 10. They're just regular numbers. They're decimal numbers, but they're numbers. They don't have an x, right? So that makes them like terms. They may not have the same natural log to them, but they're like terms because they're just numbers. They don't have an x. So we're going to put those together the same way that Courtney said we would add the 15 to the 20 because they're like terms. These pieces here are like terms because they don't have an x. They're just numbers. Okay, so we're going to move this 5 natural log of 3. We'll move it over here with addition. That technically doesn't matter which direction you go. I just moved it with addition because I wanted to get rid of that minus sign. Because I don't like the negatives. Always it gives me a chance of messing up if I do that. So on this side we got x natural log of 3. On the right side we got x natural log of 10 plus 2 natural log of 10 plus 5 natural log of 3. Okay. Now on the right hand side, one of these things is not like the other. One of these things just doesn't belong. Which one doesn't belong? The thing that's got an x, right? So it needs to go to the other side. So it's a positive x natural log of 10. So to move it, I'm going to subtract x natural log of 10. All right. I would say problems like this example may be the toughest ones that are in this section. So don't feel like they're all going to be like this. They're long problems, so that's what makes them tough. And there's several operations. So now I've moved that over by subtraction, and then the other side now doesn't have that on it anymore. It's got 2 natural log of 10 plus 5 natural log of 3. Now, here's the tricky part to this. This is what yeah, none of the rest of it was the tricky part. I know it seems like a lot, but it's not so bad once you've done a couple of these, and we'll do another one in just a second with this. All right, so on the left side, you got x natural log of 3 minus x natural log of 10. What do those two have in common? They're both have the x on them, right? So can I do a little bit of factoring with that and get x out of there? If I do that, that's going to give me x parentheses natural log of 3 minus natural log of 10. And on the other side, I hadn't changed anything, so I'm just going to copy it now. Yeah. We're almost done. Just one more step. One more step, we're done. Okay? Because now we've got x times natural log of 3 minus natural log of 10 is a number. This is a number, right? So to get rid of the number, we divide by it. So I'm going to divide by natural log of 3 minus natural log of 10. Natural log of 3 minus natural log of 10. There's an x by itself. That's what we've been trying to do this whole time. And then on the right-hand side, we got 2 natural log of 10 plus 5 natural log of 3 over natural log of 3 minus natural log of 10. And we're going to get the decimal approximation for that. Ugly looking answer, but it's going to turn into just a little decimal. It's got 4 decimal places. Okay. So 2 parentheses 2 natural log of 10 plus 5 natural log of 3 divided by parentheses natural log of 3 minus natural log of 10. A lot of parentheses there to do it that way. But in one swoop, we get the decimal approximation to be negative 8.3874. Negative 8.3874. Copy that. 3874. Yes. There. Our final answer. Finally answer on that one. Finally an answer. Okay, so again, these are the most difficult ones of the problems that you're going to see, but again, not don't freak out on them. If you'll take it a step at a time, it's not bad. We're going to do another one like that before we move on to the next one, next kind of problem. All right. Scroll up so you can still see the bottom of that. All right. So example E. Let's say we had a 4 to the 2x plus 1 equals 7 to the x minus 3. So again, we would look for the shortcut to say, can we get the bases the same? Because if the bases were the same, we could do it like that first section that we talked about with solving exponential equations or exponential functions and get the bases the same, and it works really easily. But since the 4 and the 7 don't have anything in common, we can't do that. So this is where the natural log is going to come back in. So I'm just going to write it on here and take the natural log of each side instead of writing that extra step. And then I know I'm going to do what with the exponent parts? Put them where? In the front. Yeah. That's the always going to do that kind of thing. Okay. So we're going to have 2x plus 1 and then natural log of 4 and then x minus 3 and natural log of 7. All right. And then we're going to take and distribute the number natural log of 4 to both these pieces and the number natural log of 7 to both of these pieces. So it's a distributive property next. That's 2x natural log of 4 plus natural log of 4. That was nice. And then this is x natural log of 7 minus 3 natural log of 7. Okay, now we start putting like terms on the same side. So we need all the x stuff on one side and all the non-x stuff on the other side. Okay, so if I look at this left side, there 2x, that's got an x part, so I'm not going to move that part. But this natural log of 4 here, I can get rid of. I can move it up to the other side by subtraction. And then on this side, I've got this x part here that I can move to the left side by subtraction. So that cancels that. This cancels that. And there we have 2x natural log of 4 minus x natural log of 7 is negative 3 natural log of 7 minus natural log of 4. So I've taken everything that had an x and moved it to the left side, and everything that didn't have an x and moved it to the right side. What that allows me to do then is to say, oh, okay, these two have x in common. So that means I can go x parentheses 2 natural log of 4 minus natural log of 7. One more step. That's all there is to this. One more step. What am I going to leave alone? I'm not going to mess with the x because that's what I want, right? So I'm going to get rid of this other part by division. So that's what x is equal to. Negative 3 natural log of 7 minus the natural log of 4 over 2 natural log of 4 minus natural log of 7. And we're going to get the decimal approximation for that. Okay. Again, these are the most difficult of this particular section, I believe, for the whole thing in here. I think they're the most difficult. Okay. So I'm going to use a calculator to help me get that decimal approximation. So I got negative 3 natural log of 7 minus natural log of 4. Divided by 2 natural log of 4 minus the natural log of 7. 2 natural log of 4 minus natural log of 7. Decimal approximation, negative 8.7386. If you took that decimal number and plugged it back into the original problem, if you took the rounded value and plugged it in to the original problem up here at 4 to the 2x plus 1 equals 7 to the x minus 3, it would get really, really close to one another. It wouldn't be exactly the same because it's rounded. But if you took this unrounded decimal right here and worked it as, what was the original? 4 to the 2x plus 1. So if I did 4 raised to the 2 times the answer plus 1, you got that. And then I did 7 raised to the that minus, okay, 7 raised to the that minus 1. Minus 3, not 1. Sorry. See, I get the same decimal on each side. And so I've checked that solution. This is where solving equations, that's why I like it so much, because I get an answer and I can check it in the original, make sure that it's the right answer. If I don't get the same thing on each side, it ain't the right answer. Okay, so that's, you got to be careful on that. So again, I think those are the most difficult of this particular type of problem. Let's look at one that's a little easier here, and see what we can do with it. Let's say we had if e to the absolute value of x is equal to 50. And that looks like it's complicated, but it's really actually going to work out really nice for us. Okay, because it's e as the base on the left side, it's really obvious that you can't turn 50 into e as a base, right? So don't even have to think about that too hard. We just know we're going to take the natural log of each side. And when you do that, if you take the natural log of e, remember natural log is log base e, that if I take the natural log of e, it's equal to 1. So we really end up with absolute value of x is equal to the natural log of 50. And what do we know about the natural log of 50? It's a what? It's a number. So what I'm saying over here on the left side, that this natural log, because natural log is a base e, if you take the natural log of something with e, they cancel one another out. That's what's happening. That's how I ended up with absolute value of x there. So here's where we got to remember absolute value equations. When we did those, you have to set up x equals the natural log of 50 and x equals the negative natural log of 50, because remember, absolute value is a distance away from 0. And so it could be at positive natural log of 50, could be at negative natural log of 50. So we're going to get a decimal approximation for both of those as solutions. So natural log of 50, go 4 decimal places, 3.9120. 3.9120. The negative of that, negative 3.9120. So we get 2 answers out of that, because we usually get 2 answers from absolute value equations. And both of those work in the original problem. Okay? So absolute value equations, that general idea is that you have to set whatever is in the absolute value equal to the positive of the right side and to the negative of the right side, and solve both of those out of that. So there's a kind of a mix of some things we've done. All right, so let's look at another one that has the e as the base. E to the 4x times e to the x minus 1 is equal to 5e. And at first glance, you think, oh man, the bases are the same. And they kind of are, but they kind of aren't either. On the left side, you got 2 things that are multiplied together that have the same base. So I can simplify that side using exponent rules. Even though the base is an e, it's still an exponent rule because I have the same base. If I multiply and have the same base, what do I do with the exponents? Add them together. So 4x plus x minus 1 would be 5x minus 1. And then that 5 that's in the front messes everything up. Because if it were 5 as an exponent, I could set up the equation 5x minus 1 equals 5, and it works. But it's a 5 in the front, not a 5 as the exponent. So that means I've got to use the natural log to solve this. Okay, so I've got natural log of both sides. And what happens to the natural log of e? It turns into 1, cancels out right there, and I get 5x minus 1 equals the natural log of 5e. and then I can get x by itself now, right? Because that's I got just x's over here, and I got things that don't have x's over here. So I'm going to add 1. So that's going to be 5x equals natural log of 5e plus 1. And then I'm going to divide everybody by 5. X equals natural log of 5e over 5. All right, let's just do plus 1. All of that over 5. A decimal approximation for that. Natural log of 5. Second, natural log to get the e to the first power plus 1. And then I'm dividing that answer by 5. 7219. 0.7219. A little bit different on that one, but doable. So we've seen several where we're using a logarithm to solve it. And we've been using natural log, common log to solve that. That's the most generic way to solve the logarithmic equations. So let's look at some equations that have a log already in them to finish up with. So we got logs already in the equation, and we're going to have to get rid of them so that we can solve for x. Okay, so h. Let's say we had 4 natural log of x is equal to 36. Okay, so the general consensus here is to get rid of, get the logarithm by itself or condense, together. So we want to look at that and say, okay, well, I can get rid of that 4 because it's 4 times natural log of x and move it over here with 36. So how do I get rid of that 4? Yeah, just divide it because it's 4 times natural log of x. So if I divide, I'm going to get natural log of x is equal to 9. And here's where knowing what the base is the key to being able to solve these, because it has the natural log in it to begin with. So it has a log, and in order to undo a log, you want to think about exponentiating using an exponent or an exponential. The base of the natural log is what? It's e. So to get rid of the natural log, you're going to exponentiate with an e. So that's what it's called, is exponentiating. Exponentiate with a base of e. And what happens on the left side is the same thing that happened when we took the natural log of e. They cancel each other out. And on the right side, we just have e to the 9th power. And we can get a decimal approximation for e to the 9th power. It's a number. Second, natural log to get the e, put the 9th power on it, enter. 8,103.08393. 8,103.08 something. 39. Yeah, just 4 decimal places would be 39. So there's our solution. So we're going to exponentiate with whatever the base of the log is. Okay? So if we had a problem like this, where we had log base 3 of x plus 6 equals 5. We have a base on the log of a 3, so we're going to exponentiate with a base of 3. Before we can do that, we got to make sure the log is by itself. It is on this case. There's nothing else to do. So these cancel each other out. And we got 3 to the 5th power, but 3 to the 5th power is just a number that we can work out. 3 raised to the 5th, 243. And now that's a pretty easy equation to solve. Subtract 6. 200 and be 37. And that's x. So we've got a log in the problem. We try to make sure it's isolated, and then we use that exponentiation with whatever the base of the log is. Okay. So let's say we had log base 2 of x plus 4 quantity squared is equal to 24. So this is where knowing your log properties can make life a little simpler for you from time to time. Because that's a squared in there, I can use a log property to bring this 2 down to the front, because undoing squared is much more difficult than undoing multiply by 2. So I'm going to get that down there to the front so that it's log base 2 of x plus 4. 2 times the log base 2 of x plus 4 is much easier to get rid of this 2 when it's multiplied than it is when it's squaring, right? Because to get rid of that 2, we're going to divide by it. Dividing by 2 is much easier than taking the square root of something, right? In most cases. So that's why I did that. (24) divided by 2 is 12. And now we have a log base 2 of x plus 4 is equal to 12. And I want to exponentiate that with the base of what? 2. Whatever the base of the log is, that's what that's going to become the base for my exponentiation. So these cancel each other out and gives you x plus 4. And then whatever 2 to the 12th power is. 2 to the 12th power is 4,096. Just a number. And that's a pretty easy equation to get x by itself on. Subtract 4. 4,092. So one log in the problem, get that log by itself, and then try to get rid of any exponents you might have, and then exponentiate. That's going to be the key to that. Let's look at one that maybe has more than one log in it. And this is where those properties of logs comes in. Okay, we kind of use the power rule there on that last problem. Let's look at one that maybe has log of 2x plus 1 plus log of x is equal to log of x plus 8. So this one has logs all over the place. The key to this problem is the fact that this left-hand side has an addition between the two logs. And anytime you have multiple logs on the same side, you can condense that together to rewrite them as one single log using those log properties. So what does addition turn into? Multiplication. So instead of having two logs there, I'm going to rewrite it as one log of x times 2x plus 1, which would be 2x squared plus x. So I just went ahead and did the distributive property with that because the addition turns to multiplication. And then on the other side, we got log of x plus 8. Now that I have the logarithms on each side, the same log on each side, what's the base of each of those logs? And there's nothing written there. they're base 10s. So if I use a 10 as the base, these cancel each other out. And I get this problem, 2x squared plus x equals x plus 8. So I've gotten a problem that now has an x squared in it. Because it has an x squared in it, what do I need to do to solve it? Get it equal to 0. Very good. So subtract x and subtract 8. There's equal to 0. So I have 2x squared. Positive x minus x cancels out, and then a minus 8. Well, everything's divisible by 2, so that's a GCF of a 2. Technically, I divide by 2 and get rid of it. X squared minus 4, that's a difference of squares. X plus 2, x minus 2. Set each of those equal to 0.
Your meeting is ended.
Oh, that's great. How does it end 15 minutes early? It says you're calling me. And I tried to call recent contacts and it won't let me call. last 3 examples. That's okay. I've taught this before. I can send you the video before. All right, so 4.3, section 4.3, 1 through 99. There's 100 problems in that section. 4.4 that you could do 1 through 97. 4.5, there's 105 in that section. 4.6 is the application problems, and we kind of pulled that in to the other stuff, and there's just about 50 of those that you just, those are some good practice problems that you can look at. Again, I'll send you video links, and I'll send you the labs and the quizzes that you should be doing. We will not meet on Thursday. I'll see you next Tuesday, and we'll do chapter 5 stuff on Tuesday, which is a lot of calculator stuff. Show you how to do that. And we'll finish up the material hopefully on Tuesday of next week and get you ready for the final exam, which is August the 8th at 4 o'clock. All right. Guys, have a great week and weekend. Email me if you got questions.